In this segment, I want to talk about Newton's third law. Newton's third law is, on the face of it, fairly straightforward, but it's actually, I think, the most subtle of the three laws. So recall when we first defined a force, we said, hey, a force has to have an object and it has to have an agent, right? And we said that forces are interactions between two things. So forces are interactions between two objects. Here I have a pumpkin. If this pumpkin was the only object in the entire universe, there would be no forces, because there would be nothing for the pumpkin to interact with. However, I also exist in this universe, and therefore I can apply a force to the pumpkin. Behold, I am applying a force to the pumpkin. I'm pushing on the pumpkin in that direction. Okay, now I push on the pumpkin. What always happens is that the pumpkin pushes back. In fact, I can feel on the tip of my finger, I can feel the pumpkin pushing back on my finger every time. And the thing is, there's nothing I could do to arrange to where I could push on the pumpkin and have the pumpkin not push back. There's nothing I could do. And so, what does Newton's third law say? Well, Newton's third law says that every force occurs as a one member of an action-reaction pair of forces. Very important key points here. The two members of the action-reaction pair are on two different objects, right? And so here, the objects are me and the pumpkin. I push on the pumpkin pushes on me. Two different objects. They form an action-reaction pair, the two forces do. The force on the pumpkin and the force on me form an action-reaction pair. Notice that they are on different objects, me and the pumpkin. The two members of an action-reaction pair are in opposite direction, but equal in magnitude. In other words, if I push on the pumpkin with 5 newtons in that direction, then the pumpkin pushes on my finger with 5 newtons in that direction every time. There is nothing that I could do to change that fact. This is an always type of a situation. Recall when we first introduced forces, we talked about how every force has to have an object, or every force is on an object, right? We call that the object of interest. So if my object of interest is the pumpkin, and I apply a force, then I am the agent, and the pumpkin is the object. I apply a force to the pumpkin. What Newton's third law says is that that's not an exclusive situation. There's always, along with that, the object and the agent reverse, right? So action-reaction pairs always have object and agents that are flipped. So if the one force is me pushing on the pumpkin, I am the agent, the pumpkin is the object. Then the action-reaction force pair to that is the pumpkin pushing on me. I am the object, and the pumpkin is the agent. Always, 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 forces are interactions between two things, and if one pushes on the one thing, then the other pushes on the other thing. You know, the classic example is I hit the nail with the hammer. Seems reasonable. That's how we always envision this interaction happening. But it is also true that the nail hits the hammer. The nail hits the hammer just as hard as the hammer hits the nail. Then why do they have different results, right? Well, if the force is the same on the nail as it is on the hammer, why does the nail go in? In the hammer, I hardly even feel a change in the motion of the hammer. Well, because the hammer and the nail are not symmetrical, right? They don't have the same mass. They don't have the same initial velocity. So even though they have the same force, they won't have the same acceleration. And they certainly won't have the same final velocity. So it's just the force that's the same. There's lots of other things that are different. Like, for example, this morning I was driving my car. Actually, I wasn't. I'm actually in my basement. I didn't drive anywhere. Let's imagine that I was driving my car this morning and I hit a bug. And the windshield of my car, I guess, hit the bug. And the bug splattered on my windshield. Okay, question. How does the force of the windshield on the bug compare to the force of the bug on the windshield? And why? The follow-up question is that why are our days so different? The bug, had a really bad day, and I'm here lecturing to my computer. The answer is the force is exactly the same. The bug exerts exactly the same force on the windshield as the windshield exerts on the bug. Why such different results? Same force, very different accelerations. Recall Newton's second law. Newton's second law says that the acceleration is proportional to the net force and inversely proportional to the mass. So in the case of the bug, large force, tiny, tiny mass, large acceleration, very bad day for the bug. In the case of the car, same force, very big mass, tiny acceleration. I didn't even notice it, right? I didn't even notice my car slowing down when the bug hit the windshield. I suppose on some imperceptible level, in the 11th decimal place, my car probably did slow down a tiny bit when I hit that bug, but not enough to notice. Okay, same force, different results, right? And so remember, cause and effect. Force is the cause, acceleration is the effect. Mass tells us how much of an effect we get, right? So same force on the bug and the car, different masses cause very different results. In the last segment, we talked a little bit about cars driving, and I showed you that cool picture of the funny car with the folds in the tire from it pushing on the concrete, or pushing on the road. And I had claimed in that previous segment that it was actually the force of friction that propels a car forward. And I think that we can understand that a little bit better now that we have Newton's third law to help us out. You know, we know that the force of friction on a car is forward, and that's what's pushing on the car if it's speeding up, right? And we can think of these as action-reaction pairs. The tire pushes on the road, that's fine, in the reverse direction. I think most people feel pretty good about that. But it's true then that if the car is pushing backwards on the road, then the tire is pushing backwards on the road, then the road must be pushing forwards on the tire. Action-reaction pairs. These two forces will be exactly equal and exactly opposite. And again, another thing about Newton's third law that is subtle is that this is always the case. There is nothing you could do to make it so that these force pairs were not equal and opposite, or that a force only exists. Like nowhere in the universe is there a force that exists all by itself. They always come in pairs. Walking is the same thing. You know, if I'm going to accelerate in that direction like this, I'm back. Then what force was it that pushed me in that direction? Well, it was friction, right? I pushed on the ground in that direction, and the ground pushed on me in that direction, right? Again, an action-reaction pair. Okay, let's do a quick clicker question type example. 10-year-old Sarah stands on a skateboard. Her older brother Jack starts pushing her backward, and she starts speeding up. The force of Jack on Sarah is what? Greater than the force of Sarah on Jack, equal to, or less than the force of Sarah on Jack? Why don't you pause the video, see if you can't answer this question. I will see you on the other side. Okay, well, Newton's third law says that if Sarah pushes on Jack, then Jack pushes on Sarah. And those forces must be equal and opposite, and there's nothing we can do to avoid that. Does it matter that, we assume Jack's probably bigger than Sarah? No, it doesn't matter. Does it matter that Sarah's on a skateboard and Jack isn't? No, those forces are still equal and opposite. So, why then does Sarah start rolling off and Jack presumably just stands there? Right? So they have different results. How can the force be the same? Well, their masses might be different, and so that might give us different results. But also, this is only talking about one of the forces on Sarah and Jack, right? So if we were to put Jack here, and we'll put Sarah here, and we were to draw a quick free body diagram for these two, then what would we see? Well, maybe you should try and do this on your own, and then you can check in and see how you did. For Jack, we should have the weight down, the weight of Jack, and the normal force. And those should be equal because Jack is not accelerating in the upward direction or the downward direction. Sarah, we're not done with Jack, but let's go ahead and add those to Sarah. Sarah also has a weight and a normal force. Those are also opposing, presumably a little smaller if Sarah has a little less mass, if Sarah is a little not as big as Jack is. Okay, let's do the force of Jack on Sarah and the force of Sarah on Jack. Well, Jack pushes on Sarah. Okay, if Jack is here and Sarah's there, then Jack is pushing in that direction. And so we'll say this is the force of Jack on Sarah, right there. Well, Newton's third law tells us that the force of Sarah on Jack should be exactly equal and opposite. We'll put it right here. That is the force of Sarah on Jack. Exactly equal and opposite. Now, Sarah's on a skateboard. Does she have friction? Sure. It would be very small, though, right? So Sarah has a tiny amount of friction. And it would be, rolling friction, which we really haven't talked about too much yet. In fact, we're going to dig into friction just a little bit more in Chapter 5. But, suffice to say, she's got some rolling friction, right? A skateboard rolls with low friction, but not none. If you give a skateboard a push, it eventually comes to a stop. So that's what Sarah's free body diagram looks like. Well, how about Jack? Assuming that Jack is just standing there and didn't accelerate at all, that means there must be friction on Jack, but it must be exactly equal to this force, because Jack did not accelerate. And if Jack is standing there in his sneakers, then that is static friction, because there is no sliding. And these should be equal and opposite. Looks like they're pretty close. Make it a little bit longer. Oh, that looks a little bit better. These are equal and opposite. Okay, there we go. There's our free body diagrams. And now we see why Sarah has a different result than Jack does, even though these two forces are always equal and opposite. Here's another one. A book is at rest on a table. Which pair of forces is an action-reaction pair? The weight of the book and the normal force of the table on the book. Is it the weight of the book and the weight of the table, or is it the normal force of the book on the table and the normal force of the table on the book? Pause the video. I'll see you on the other side. Okay, this is a little bit of a tricky one. Here's our situation, right? We got a table, and here's my book. It is, of course, a physics book. There's my physics book sitting on a table. Apparently it is a small table and a large book. Okay, let's go through this list. The weight of the book and the normal force of the table on the book. Do those two forces exist? Well, sure. If I was going to do a free body diagram for the book, then we would have what? The normal force, let's add on book here. And then we would have the weight, and of course that's the weight of the book, right? So we've got the weight of the book down, and we've got the normal force up. Are those equal and opposite? Yeah, they are. Are they a force pair? They're not. They're not a force pair, though they are equal and opposite. Why not? Well, first of all, they're on the same object, right? And so this says, the weight of the book and the normal force of the book, those are both on the book, right? Those are both forces on the book. But Newton's third law, it always refers to forces between two different objects. It's always an interaction, right? And so that can't be it, right? Because those are both on the same object, right? So even though we don't maybe know what the answer is yet, we know it can't be A, because there's no way that Newton's third law force pairs are on the same object. It just doesn't work that way. How about the weight of the book and the weight of the table? Well, we could do a free body diagram, I guess, for the table. So this is for the book. For the table, what would we have? Well, we'd have the weight of the table. Well, the table certainly pushes on the book. So let's just call that table on book. And the book, I guess, pushes on the table also. And so we'll just kind of add that right here. And that is actually the normal force, right? So this is a normal force because it's from a surface, right? This is book, sorry. So that's book on table there. And it's a normal force. Okay. Well, the weight of the book and the weight of the table, those are both in the same direction. And presumably, the table is probably heavier than the book. At any rate, I don't expect them to be the same. So they're not in the same direction. Or excuse me, they're not in opposite directions. And they don't have the same magnitude. And it can't be B. Well, either I've asked you a horrible question or the answer is C. And indeed, the answer is C. It is the normal force of the book on the table and the normal force of the table on the book. Right? Again, let's look at this force right here. This force right here. The normal force on the book, What's the agent? What's the object? Well, the agent is the table, and the object is the book. So, for the Newton's third law force pairs, we should switch those. Right? The agent becomes the object becomes the agent. We could think of this as if the table pushes on the book, then the book pushes on the table. So our Newton's third law force pair is here and here. Is there a Newton's third law force pair to this force right here, the weight of the book? Well, the answer to that question is always yes. If I ask you a question, is there a Newton's third law force pair to go with this force? The answer is yes, because Newton's third law says that forces always come in pairs. What is it? Well, I think in order to answer that question, we need to wrap our brains around what's the object, what's the agent. What is the agent that's causing there to be a gravitational force on the book? Well, it's the Earth, right? It's the Earth. So the Earth is causing the gravity that is pulling on the book. Some people, when I ask that question, what's the agent? People will say gravity is the agent. Ooh, gravity is not a thing, right? Forces are interactions between objects, between things that you can hold in your hand, right? So forces are between objects. Gravity is not an object. Gravity is the name of a force. It is not the agent that causes a force. What is the agent? It's the Earth, right? So we can interpret this weight of the book as Earth pulls on book. What's the Newton's third law force pair? Book pulls on Earth. And it would be a gravitational force. That's another thing about Newton's third law force pairs. They are always the same type of force. In other words, if we started this conversation talking about the normal force on the book. The Newton's third law force pair to that will be a normal force of the book on the table, right? So force pairs are always the same type of force. So, if gravity pulls on the book, that is the Earth pulling on the book. That means that the book pulls on the Earth, also a gravitational force. So, I have a weight of about 180 pounds, and we can interpret that as the Earth pulls on me with a force of 180 pounds. However, Newton's third law says that I pull on the Earth with an exactly equal and opposite force. Therefore, I am pulling on the Earth with 180 pounds of force also, which makes me feel important. So I like that.